I want to thank first the organizers for this wonderful conference and for having me here. I'm Alessandro Lupi. I'm an assistant professor at the University of Insubria in Como. You can see a beautiful image of Lake Como in Italy. And today I'm going to talk about, well, seed formation and dynamics in high-redshift galaxies. And then at the end, I will say something more about Super Eddington. And this work I've done in collaboration with people you see here. I don't know why the I is missing there. But so let's start. I'll give a very brief introduction since Elisa today, but also Iago, and yesterday and the day before there were beautiful introductions about the topic. We know that from observations, we see very massive black holes at very high redshift in massive galaxies, and these observations put strong constraint on the initial mass. Of course, to get these constraints, we have to trace back what the initial mass of the black hole should be. And of course, since we are only observing a snapshot of the universe, we can only do it by making some assumptions. For instance, a typical assumption is the black hole is growing continuously at the Eddington rate, and so we can go back and see what would be the initial mass. Of course, this is up.
The middle button of the.
Oh, okay.
Yeah.
Okay. So of course we can do that, and we can see that the initial mass should be between 100 and 10 to the 4, 10 to the 5, depending on. And this is consistent with different models for the formation of seed black holes. And so in order to test this, we should, if we trace this back, this means that we should look at lower mass objects, and this means also ideally lower mass galaxies. So now with JWST we can do it, and you can see the Maiolino results where actually even at lower mass, these black holes seem quite massive. So we have not solved the problem. We are not probing yet a mass close to the initial seed unless these black holes formed already with 10 to the 7 solar masses, which is a bit unlikely to me. So we should go back even further and look at the early stages, so even lower system. Of course, this has some advantages. We can probe black holes that ideally are close to the initial mass, and the low mass galaxies are extremely abundant in the universe, especially at low redshift. Of course, there are some problems with this, that typically low mass black holes are harder to detect, and even low mass galaxies are less luminous, so harder to observe, even in the local universe. On top of this, if the galaxy is cored, we might expect this black hole to wander around the center. And also, as Daniel showed and many simulations show, that supernova feedback might suppress the initial growth of this black hole. So this may give some issues also with this simple picture of continuous Eddington accreting black holes. So how can we study this? Well, we can use simulations. And what we can do is we create we use a cosmological model. What is the problem? If we want to study low mass black holes, we need very high resolution. Why? If we want to study the dynamics of this black hole, understand if they sink to the center and then they are able to accrete, if the black hole mass is between 10 to the 2 and 10 to the 4, we cannot use a simulation with 10 to the 6 solar mass resolution. And as Michael Tremmer showed, and also Bob Pfister, when the black hole mass is comparable or smaller than the dark matter or stellar mass, the dynamics is not resolved. So if we want to study low mass black holes, we need very high resolution. In the dark matter, for instance, here you can see we should need something like 100 solar masses per dark matter particle. But this means that the baryonic mass we can resolve is not anymore a large mass that can be sampled, assuming that we form a population of stars. But we have to start tracking single stars, especially single massive stars, because the mass resolution is comparable to the mass of a single star, 10 solar masses or so, which means that we need a new model for star formation, a new model for stellar feedback that tracks every single star. And of course, if we want to study black holes, we need to go to very low metallicities. And when we are at very low metallicity, we cannot use the simple description of the gas thermodynamics. We need primordial chemistry, and a very accurate primordial chemistry, as Simon Glover showed in many of his papers. And of course, if we want to study black holes, we need accretion and feedback of these black holes. Unfortunately, there is an additional complication. Low mass black holes, when they accrete, they have an emission spectrum that peak in the X-rays. And this means that if we want to follow the thermodynamics correctly, we need to include X-ray photochemistry, which is extremely complex because high energy electrons can ionize further and produce secondary ionization. So we should put everything together and build this model. And this is what we have tried to do. We have prepared a zoom-in cosmological simulation of a dwarf galaxy. It's an initial test. We want to expand the model to more massive galaxies, but for now, we have a halo of 2 × 10⁹ solar masses at redshift 6 with 35 solar masses per barrier. And we've run the simulation using the Gizmo code. And in this model, we have included non-equilibrium chemistry with many different processes. We are including primordial species, metal elements up to iron, that is very susceptible to, sensitive to the hard radiation, photochemistry, X-ray chemistry, with on-the-fly radiation transport. We have included star formation in the POP3, with the POP3 IMF and the POP2. And of course, since the mass is in between the mass you use when you do molecular cloud simulations and the mass that you use when you do large-scale simulations, in some cases, the mass we form is smaller, as a lower mass compared to the gas mass. In some cases, it's larger, so we have to combine different prescription to sample these stars. In one case, we directly sample the mass and extract it from the gas mass. In the other case, we convert the protostar into a sink, accrete the mass we need, and we form a more massive object. We also included completely revised models for stellar feedback, including wind, supernovae, radiation from POP2 and POP3 stars, using the most up-to-date stellar evolutionary tracks. And we also accounted for POP3's black hole formation. And for black holes, we included, for the moment, Eddington limited accretion, kinetic winds coming from the radiation coupling with the gas, and relative feedback on top. And of course, black hole mergers. And this is a movie of the simulation. It goes down to redshift 5.7. You can see the formation of the halo, and at some point you'll start seeing the formation of the first stars. This is the first clump that forms stars, and you can see the powerful effect of supernovae. The green stars correspond to stars that at most end up in neutron stars at the end of their life, and the black dots correspond instead to black holes, POP3 remnants or POP2. And the size of the dot depends on the mass of the black hole. So the largest ones are the more massive, the smallest ones are the lower mass black holes. And you can see how this galaxy forms. This is around redshift 6. And you can see now that if we look at this distribution of the stars and black holes, in the central kiloparsec, there are many POP3 remnants, many black holes, and also stars. Okay, the blue circle corresponds to 1 kiloparsec. When we measured the distribution of these black holes, we found that a few of them were inside the central parsec of the galaxy. In this sense, these black holes are not wandering around the center. At this initial phase, unlike some studies predicted that you form 1 POP3 remnant per galaxy, in this case, we have many POP3 remnants. And they come from the merger of very compact structures that form in the early universe, and then they merge together, but the size of these galaxies is small, so also the dynamical friction is more effective because when they merge, they are already close inside a few hundred parsecs. And when we look at the distribution, we can see that our model is able to capture the two populations of black holes. You can see in the right panel, you can see the remnants of POP3 stars, around 10⁵ solar masses there, and the population of lower mass black holes that form from POP2 stars. And you can see that they are separated. There is a gap in between. You can see that some of them merge together. Okay. This is due to the fact that in some cases, we have very small clumps where two massive stars form. They are very close, so when they become a black hole, very quickly, by dynamical friction, they merge together. Of course, this is at the limit of the simulation we have. Of course, we are not accounting for dynamical friction and the shrinking of the binary in a proper way. This is for the future improvement, but still, we are anyway able to probe the mass of the initial POP3 remnants. And you can see here the total mass in the galaxy. You can see that at these early stages, most of the mass is in black holes. 10⁴ solar masses is in black holes, and only 10 to the 3 solar mass is in stars. And there are many black holes around 10 to the 3 solar masses. So in the end, even with POP3 remnants, if we account for the most up-to-date IMF for POP3 stars, we can have black holes around 10 to the 3 solar masses, a bit lower than what John found for heavy seeds, probably comparable to the black holes forming in nuclear stellar cluster. All black holes seem to be around 10 to the 3 solar masses. And so what next? Starting from this work, we would like to extend it to model also medium weight black holes and heavy seeds. And of course, this is work in progress, so stay tuned for more results. And now, before finishing, following Martha's suggestion, I would like to show you some results about what happens later. So let's assume that we have our black hole, heavy seed, light seed, medium weight, whatever you like the most. What is happening later? Because we need to grow these black holes, starting from these masses around 10 to the 3, 10 to the 4. And we know from simulations, especially, that supernova feedback stunts the growth of these black holes. And you can see the results from the New Horizons simulation Martha showed. And you can see that the low mass black holes in low mass galaxies struggle to grow. But could Super Eddington alleviate this issue? What we did was to test what happens in a massive galaxy at redshift 6. This is a quasi-Ross progenitor. So we ran a zoom-in cosmological simulation. Here, the resolution is much lower. We cannot do follow single stars. But we now included Super Eddington accretion, also accounting for the powerful jet outflow that develops during Super Eddington phase. And we included 3 regimes, similar to what Doug showed. And this is what we got. We got that, of course, we had to assume how much the magnetic field was close to the critical value. We assumed 2 values, the critical one, the mad limit and half mad. You can see that we can reproduce some phases where the black hole is constantly accreting at Super Eddington rates. Of course, there are large fluctuations because there is a burst of Super Eddington accretion, strong feedback, the gas is heated up, the accretion goes down. But since the gas is dense, there is no way to expel this gas. So as soon as cooling takes over, the gas falls back and accretes again. And then this leads to a growth that is much faster. And so you can see that when the black hole starts growing, in both cases, they can gain 1 or 2 orders of magnitude in a few tenths of mega year. Of course, where do we put this? How can we put this in the galaxy black hole mass relation? Unfortunately, our black holes, when they formed, they were not at the center, so they had to spiral down, and this delayed a bit the initial growth. But when they settle in the center, then they can grow very quickly. And so, especially in the half-mad case, we can approach the overmassive black holes that we can see at high redshift. And we also checked, and then I finish, that, of course, in our simulation, we assumed the constant spin for the black hole. We didn't include a spin model, and we compare with what Angelo showed via semi-analytic calculation. We found that our feedback was probably too strong because the average spin during the Super Eddington phase should be 0.3, which means a factor of 4 weaker feedback. So even faster growth, ideally. And with this, I conclude.
And here?
Thank you. Thank you, wonderful talk. So since you have many black holes within the central kiloparsec, which are presumably going to merge, and you're in a low mass halo, then would we run into the issue of kicking out the black holes to recoil kicks?
It's possible. Of course, we have not included recoil kicks, so it depends on how strong the recoil kick is. And this, of course, depends on the spin magnitude, the spin direction, the mass ratio of the 2 black holes that are merging. So it's something that we would like to include in the future, but so far we don't have it because the model was very complex. It took a long time to run, but yes, it's something we want to address.
If you go back to one of the slides that you had for the mass of the black holes and the stars, I think it was. Yeah, that would be back to the way. Yeah, the black holes go shooting straight up there at there's nearly a vertical line there at like redshift 10.5.
Yes.
What's happening there?
Well, in that case, I haven't checked in detail there, but I suspect there are mergers ongoing among pristine halos that lead to a boost in the formation of POP3 stars. And these POP3 stars can be more massive than POP2, and so they can lead to a larger population of black holes.
So a starburst, basically. Or something.
Yes.
All right. Okay. Cool. Okay. Thanks.
But I have to check everything. Sorry.
One last question.
Thanks. Great talk. So I was wondering if you were to calculate the total mass of POP3 stars in your galaxy, what fraction of that mass is actually ending up as the total black hole mass of your POP3 seeds?
Well, you can see here that if we take the POP2 remnants, black holes, they are a few and all below 100 solar masses, which means that most of the black hole mass is POP3 remnants. Okay. So, of course, but I can check. I haven't checked yet. The simulation ended a few months ago, but I haven't had time to analyze it in detail yet. But I'll do it. This is something I want to look at, of course. Thanks.
Thank you, Alessandro, again.
I find my.
So now we have Magdalena Siwek talking about signatures of circumbinary disk physics in massive black hole binary populations.
Thanks. Can I have one of those? Thanks. Thanks for having me and for making it to the end. So I want to talk about circumbinary disk physics and how the physics that we see in hydrodynamic simulations of these systems can actually imprint itself on the massive black hole binary population that we're about to see. So I include this slide. I don't think it's necessary at this point, but we think that massive black hole binaries form as a result of the mergers of galaxies, right? What is less clear is the post-galaxy merger evolution. So we think that at these larger scales, when the two black holes are not yet bound, dynamical friction and cell scattering act to bring both of these black holes towards the center of the newly merged galaxy. But then potentially, depending on whether you believe in the final parsec problem or not, those processes might become inefficient at parsec scales. And at those scales, it's also possible that a circumbinary disk forms around the binary system. And so the role of the circumbinary disk is often reduced to this mechanism by which binaries shrink, right? But today I really want to convince you that it does more than this. So the circumbinary disk can alter the population statistics of the massive black hole binaries, regardless of whether it solves the final parsec problem or not. So finally, when the binary system reaches 10 to the minus 2 parsec or below, gravitational wave hardening will take over. And then we will get these gravitational waves that pulsar timing arrays may have detected and that we hope to see with LISA. Today, I really want to zoom in on this middle phase here. I want to talk about the circumbinary disk-driven phase and the physics at play, and how we can use this physics to project the properties of the massive black hole binary population. So how do we do this? We need large-scale parameter studies of circumbinary disk simulations. And so to solve this problem, or to get closer to a solution to the problem of how circumbinary disks interact with their central binaries, I ran a very large parameter study where I looked into, and I'm going to try and use is this the pointer?
Switched on.
Is it switched on? I'm going to point with my hand, if you can see. So in order to illuminate this parameter space better, I ran a large suite of simulations where I looked into binaries with different mass ratios. So Q is the mass ratio of the system, and E is the eccentricity of the system. And so oh, thank you. And so I looked into mass ratios ranging from 0.1 to 1 and eccentricities ranging from 0 to 0.8. And there's a bunch more points in between here. I'm only showing a subset of the simulation suite. And so the purpose of this really was to gain evolution rates. So the change of the mass ratio, which is a result of preferential accretion onto the secondary, the change in the semi-major axis, which can be positive or negative, like Elisa alluded to, and then also the change in the eccentricity of the binary orbit. And so one really exciting result from those simulations has been the discovery of an equilibrium eccentricity. So I published this in my 2023 B paper, but a student I'm working with has made a much nicer plot. So I'm showing that one. And this plot here shows the mass ratio of the system on the bottom and then the eccentricity on the top. And he's kind of showing the tracks on which binaries will move to get to the equilibrium eccentricity here. So the equilibrium eccentricity is this point essentially where the binary wants to live. Any eccentricity higher than this and it will circularize, and any eccentricity lower and eccentricity will be increased. So it's just really a sort of equilibrium branch, and all binaries move towards that. Now the blue and the red shaded region tell you whether it inspirals or outspirals as it moves towards this stable branch. Okay, so now next we want to understand, does this actually matter for massive black hole binary populations, right? And so to apply this physics to a reasonable sample of massive black hole binaries, we extracted just under 3,000 massive black hole binaries from the illustrious simulations and essentially evolved them in semi-analytic models using dynamical friction, stellar scattering, now circumbinary disk torques, and gravitational wave hardening. And we essentially see how these binaries evolve and merge over time. And we can then also extract information about the gravitational waves they emit along the way. Now, this video that I'm about to play shows the mass ratio and the eccentricity of this massive black hole binary population. And you can think of this at the point when the binaries have reached roughly subparsec separations, but for reference, here's also the gravitational wave frequency at which they would be emitting at that point, if that's your language. So the first video here will show how the eccentricity versus mass ratio evolves if no circumbinary disk physics is applied. So you can see these points move slightly upward, which is a result of stellar scattering increasing the eccentricity. And then they fall rapidly down because gravitational wave hardening results in circularization of the binary orbit. Okay, so now what happens if we actually have a circumbinary disk? I'm going to show this video a few times, but if we do have a circumbinary disk and we apply the physics that we've discovered in our simulations on this plot here, you can see that the binary systems actually move towards the stable branch very quickly. So they move there even before they reach the pulsar timing array regime. And then as gravitational wave emission becomes efficient, they also start to circularize, but they do so in a very ordered way, right? So I'm going to show this again. Binaries move to the equilibrium branch, but also they move to higher mass ratios and cluster sort of over here. And then gravitational wave circularization takes over and they move towards lower eccentricities. Now, we can look at this, as a picture of the distribution that will be seen in pulsar timing arrays. And we can see that we actually recover the circumbinary disk signature, eccentricity versus mass ratio that we found in our simulations, whereas no circumbinary disks are present, really have a uniform distribution of eccentricity versus mass ratio without much structure. Now, if we then look at this same plot, but with a log axis, we can see more structure, right? We can see that on top of the circumbinary disk signature relating mass ratio and eccentricity, we also see that the low mass ratio space is depleted, and that's a result of the preferential accretion of gas onto the secondary. We can also see that mass and eccentricity are inversely related, right? So you see these blue dots here are the higher mass black holes and the red are the lower mass black holes. And I can talk more about why this is, but we see this very clear ordering. Now, those are the binaries in the PTA regime. We can then also move to the regime where we'll actually resolve the population and we'll expect to see individual binary AGN candidates. And because PTA and MSST frequencies sort of overlap to a good degree, we see that the population really retains that characteristic that I discussed earlier. Okay, so I think I'll finish here. I really want to point out that second-body disk physics is an important aspect to the small-scale dynamics of massive black hole binaries. And I would like you to look beyond the final parsec problem because there's a lot more to discover. In future work, I'm hoping to extend this to lower mass black holes, which, as we learned, may live in gas-rich galaxies and may actually retain the second-body disk signatures better. And I'm also currently looking into multi-messenger transients, so accretion signatures. I'm very excited about spins. How does a second-body disk affect spins? We don't know. And obviously binary agent feedback. So thank you for your attention.
Thank you very much for finishing very much on time. So we have time for
I am German.
this is one.
This was super cool work, and I was really interested in this talk. I'm curious about, so in what you've shown, you've, I guess, been always assuming that there is a circumbinary disk. Is there always a circumbinary disk? Do you kind of incorporate information about the gas environment from Illustris when you're doing the simulation, or do you kind of like presume that the disk exists?
So I presume that a disk exists at sub-parsec scales, but I changed the Eddington fraction. So what is really exciting about this is that I think Elisa pointed this out, at very low Eddington fractions, there's hardly any contribution to hardening from circumbinary disks. The same is not true for eccentricity evolution. Even at 1% Eddington accretion, we see the same eccentricity versus mass ratio signature. So this is really a very fast and efficient process, and you don't really need much gas. You need the occasional inflow. That's pretty much it.
Thanks, Magdalena. There's really cool work. So I was wondering if the approach to that universal relation that you showed for the circumbinary disk, does that have a significant impact on the timescales at which it reaches the gravitational wave hardening regime?
You mean what do you mean by approach? Like
the fact that it gets to that universal eccentricity mass ratio relation, does that have any impact on the gravitational wave? Would that, as a consequence of that, would it lead to the gravitational wave phase sooner or later?
Oh, I understand. Yeah, so I didn't get to show this. I do have an additional slide, if I may. What determines if the binary gets to the gravitational wave regime faster or slower is really the change in the semi-major axis. And what we also discovered is that as the binary lives on this eccentricity branch, most binaries actually in spiral. So you can kind of forget about the outspiraling solution, because in steady state on the branch that we discovered, okay.
Please mute yourself on Zoom.
As the binaries move to the branch, they actually go into the regime where in spiral always happens. So that leads them reaching the gravitation wave regime slightly faster. And then to top this off, when they reach the gravitation wave regime, the sign switches again, and they live in the gravitational wave regime longer. So they boost the overall gravitational wave emission for those two reasons. I hope that made sense. If not, I can explain in more detail later.
I will ask a quick question following on what you asked. So if you go to lower accretion rates, the accretion disk should change. Instead of being, a thin disk, should really completely change structure. Is this something that can be taken into account, or is the assumption of, a thin disk and a strong ingredient in the models?
Yeah, that's a great question. I would love to look into this more. I'm planning to run more sophisticated accretion disk models. I'm finishing my PhD. After that, I'll have time. But right now we assume a thin disk, but it's a very good question.
More questions?
Thanks, super interesting. So I missed what's the physical reason for this equilibrium eccentricity? Why the systems evolve to this super interesting relation?
So it's essentially a balance of co-rotation and Lindblad resonances that causes this. There have been some older papers 20, 30 years ago that hinted at this, but we showed this hydrodynamically. But the reason really is a balance of two different types of resonances that boost and circularize eccentricity.
We have still time for questions.
You didn't put tilted discs in your future work.
I know. Oh no.
Is that just
Sorry.
lack of personal time, or is there a
No,
reason we shouldn't
there-
prioritize that?
Actually, I'm planning to do that in the spring, so
Great.
I didn't want to get scooped by you.
So wonderful. Any more questions? You see, it's great when you finish on time because then you have time to answer questions.
Actually, one of my questions, sorry.
Well, sometimes you can answer questions.
Thank you very much.
Okay, so I think we can continue. Thank you very much again.
Yes.
So now we continue with you and me, modeling the assembly and coalescence of supermassive black holes over the cosmic history.
Hello, everyone. Thanks for having me here. Today, I'm going to talk about modeling the assembly and the coalescence of supermassive black holes over the cosmic history. So mostly it's the predictions from the Astrid simulation. Here, I will start with a brief overview of the Astrid simulation. It is a large volume, high resolution cosmological simulation with box size of 250 megaparsec over H and the particle load of 5,500 cube. So compared to simulations of the similar volume, Astrid features maybe the highest resolution and also the largest particle load and probably the highest expense. So far, Astrid has cost over 400 million CPU hours. It's run on the Frontera supercomputer started at 2020, mid 2020, and it's currently go down to Redshift 1. We expect to reach Redshift 0.6 by the end of this round of this year's of allocation. But don't ask me when I will go down to Redshift 0. I don't have a good timeline for that. So here's the inventory of the subgrid models applied in the Astrid simulation. Our source code is public. Each commit is public. All the bugs and the fix to the bugs are also public. So I will not go detail into this subgrid physical models. One of the primary scientific goal of the Astrid simulation is to look at the black hole assembly and the coalescence over the cosmic history. So here's the subgrid models we did for the black hole seeding, accretion, feedback, and dynamics. As Nian Yi nicely reviewed in her talk previously, that in Astrid simulation, we upgrade the black hole dynamics models with a subgrid dynamical friction model from the Francesca formalism that we use subgrid model to model the unresolved dynamical friction force from the unresolved stellar structures, so that we can trace the black hole mergers along with the galaxy mergers with higher fidelity. And on the right, there's a cosmic evolution of the quasi-luminosity function predicted by Astrid compared to observations. It's in general a very tricky game to play. We are slightly off at the bright end, but overall, asteroid makes a reasonable prediction of the black hole assembly over the cosmic history. So here is a black hole mass function as a function of redshift, and those dashed lines are some observational predictions. So the primary feature of asteroid is the large dynamical range it covered. So the high resolution of asteroid simulation allows us to probe the black hole population in slightly lower mass band to this intermediate mass black hole regime. So as Melanie nicely reviewed yesterday, that we see the black holes in the mass range from about 10 to the 4 to 10 to the 6 solar mass with halo and the galaxy-based threshold, so that we can predict the population of the intermediate mass black holes and study their coalescence. And the large volume of asteroid also allows us to probe those very rare extreme regions that can harbor the quasar pairs and the triplets and the ultramassive black holes. So I will talk a bit of this massive end first. So here, this is a gallery of those bright quasar and AGNs residing in the large overdensities of the cosmic web. So at this epoch of the cosmic noon, which features the most active star formation and AGN activity, we have, and also the galaxy merger happens most frequently, we can have this statistical population of the AGN or quasar duals and the triplets. So here, this is basically the number density of quasars as a function of redshift and the population of the dual and the triple quasars. Roughly, we predict 1% of the quasars at cosmic noon are in the dual systems, and about the fraction of the triple quasar systems are order of 10 to the -4. Potentially, probably the most interesting feature for those quasar multiplet systems is their potential to merge. So here is we look into the brightest quasar triplet systems in the entire simulation. This is a quasar triple system at cosmic noon of redshift 2.7. And each of those black holes are super bright, and their host galaxies are all on the order of 10 to the 11 solar mass. And actually, there's observational analogs for those quasar triple systems, though they're extremely rare. So what happens to these systems that is really interesting is that this very bright quasar triplet systems undergo a very violent merger, very violent merger events with each other within a very short period of time. So on the right, we're seeing the evolution of the black hole mass and the bolometric luminosity of those three black holes and their mergers. So the black holes merge with each other within only 150 mega-year period of time. And through this violent mergers of their host galaxies, the systems undergo a very short period of active gas accretion that is near Eddington, and that powers the most luminous quasar in the entire simulation that approach a few times 10 to the 48 bolometric luminosity. And after this short period of close to Eddington accretion, the end product of this violent merger is a ultramassive black hole that with mass approach 10 to the 11 solar mass. And the end product of this violent merger is a rapidly quenched massive galaxy that evolved passively over the cosmic time. So we had an interesting conversation with Julie yesterday about the potential to detect those ultramassive black holes in the BCG clusters at current day universe. So these systems reside in a 10 to the 14 solar mass halo, which is the progenitor of the BCG clusters. And if we look at the M black hole and star relations, we see that the end product of this ultramassive black holes reside align with the extrapolation of the black hole and star relations. And we also investigate. There are a handful of ultramassive black holes in astro simulations, and we backtrace their evolution phase. And we do find that most of those ultramassive systems has undergone this triple stage that can be observed as a quasi-triplet. So the implication is that the ultramassive black holes harbored by the current BCG clusters are likely to have assembled most of their mass at the epoch of the cosmic noon, where the most violent galaxy mergers occurs, and they evolve passively down to the current day universe. So there's a caveat here that it's not the mass of the merged black hole itself, but the active gas accretion phase driven by the galaxy merger that makes the dominant contribution to the black hole to the black hole mass budget. So here is analysis of the mass fraction of the black holes contributed by the gas accretion from the black hole merger and from the seed mass. And we can see that the pure black hole merger, the pure black hole mass from the merger itself makes a subdominant contribution, while it's still the gas accretion that makes the dominant contribution to the black hole mass budget. So I will quickly go through another side of this mass spectra of the population of the intermediate mass black holes and the wandering black hole populations in asteroid. So as previous talk nicely go over this, we know that from the galaxy mergers to the eventual coalescence of the massive black holes, it's a long and arduous journey. So in the astro simulation with our numerical resolution of 1 kiloparsec scale, we numerically merge the black holes once the two black holes are gravitationally bounded to each other after the subgrid dynamical friction dissipate their relative kinetic energy. So while this strict merger criteria has a profound implication for the black hole population, especially in massive systems, the question we want to ask is what happens to the black hole that fail to merge above the resolution limit? So a typical case is that the tidal stripping of the satellite galaxies when it falls into the massive halos will strip the stellar material away from the central black holes, and the black holes are inefficient to merge onto the central black holes. So the fate of those black holes is that they will start to wander in the center of the halo. So here's a movie showing the origin of the wandering black holes. You can see that I will play this again. So this red trajectory traces a tidal disruption event that the central black hole got its stellar host tidally disrupted and got ejected from the center of the halo. So here I'm showing a typical picture of a very massive halo in the astro simulation. You see all those cross are the black holes. And in massive systems in the astro simulation, we have hundreds of those wandering black holes. They are basically the relics of the hierarchical structure formation that we naturally expect if we cannot efficiently merge the black holes with each other. So I will not go through details to that. So there are some statistical analysis of the occupation fraction of the wandering black holes. And the chance that we detect those INBH came from the hyperluminous X-ray sources when those wandering black holes travel through pass through the center of the gas-rich stellar centers. And also there are possibility to detect the merger of those INBH in the center of the satellite galaxies. And that can fall within the LISA sensitivity curve. The final add-on point I want to make is that the same procedure of the tidal strip, I'm sorry, can also explain the overmassive of the black holes in today's universe. So here I quickly show like how we how we are able to make a overmassive black hole of the Leo 1 system, which is the most distant dwarf spherical galaxy and associated with the Milky Way, but features a overmassive black hole in the center. And the tidal strip event can produce those systems as it's like a halfway goes through the wandering black hole process. That's the end of my talk. I'm sorry for that.
Thank you very much. Only sorry that we will only have short time for questions.
Hi, thanks. Can you hear me? Yes. Thanks for the talk. So maybe I missed something, but I thought that triples don't merge. There was a talk earlier that said they don't, and you said they do. Maybe I missed something.
So this is a very massive systems that features very deep potential well. So I think the triple doesn't merge, mostly happens in like more like chaotic systems of like satellite galaxies, and the triple of the less massive black holes. They are more likely to stall instead of get efficiently merged because they are not embedded in dense enough star environments.
Thanks.
Just usually triples help black holes to merge during the chaotic interaction because of quasi-Lidov mechanisms. Once you form a binary. More questions? Yeah.
Yeah, I agree with Matt on the triple systems. It should help them to merge. But actually, I was wondering, when two black holes merge, they lose about 5% of their mass due to gravitational wave emission. And I didn't see you mention that anywhere here, but you are worried about scales of like 10% of the black hole's mass coming from other processes. So I'm wondering how you could, or if you have baked that into your calculations.
Yeah. So the merger in the cosmological simulation here is still a very numerical thing. We just directly add on the black hole mass without taking account of the mass loss from the gravitational radiation. But the 10% thing I was referring to is more in the context of does black holes grow by merger or by the gas accretion? So the answer from the asterisk is like mostly from the gas accretion, but the gas accretion can be driven from the galaxy merger events. So there's like the galaxy merger and the black hole merger are two separate things. That's the point of that 10% mass budget from the black hole merger. I don't know if I answered the question to that.
Anyway, we have run out of time, sorry. So let's thank again the speaker. So we now get to the last session. Which is the next page? That I don't know. I have to press it. Should I start internet just show? View. Bottom screen. Oh, this is a pointer, I guess. Okay, great. So we conclude this session with Kunyang Dili Li on the detectability and coalescence fraction of kiloparsec scaled Willigian.
Thank you, Marta. Hello, everyone, and thank you for staying to the very end of the meeting. My name is Kunyang Li, and I'm a postdoc, a first-year postdoc, Marta student at IIP, working also with Yuan Dubois on the massive black hole binary dynamics subgrid model in Rams's cosmological simulation, but that's my current project. Today, I'm going to talk about my previous project on the detectability and coalescence fraction of kiloparsec scale UAGNs, which I did at Georgia Tech with Tamara Bogdanovich and David Valentine as part of my PhD thesis. That's not the clicker, that's just a pointer. Okay, this is the clicker. I guess.
Click in the middle button.
Middle, which is not working. Okay. Okay, I'm gonna flip. Yeah. Right, sorry about that. So observational searches for kiloparsec scale DOE-GNs is crucial for understanding the role of mergers in the evolution of galaxies. And furthermore, these kiloparsec scale DOE-GNs are also very important parent populations of merging massive black hole binaries, which are important sources of low frequency gravitational waves. So understanding the population of DOE-GNs is necessary and important for determining the future expectations for gravitational wave detectors like LISA. However, observation searches have only uncovered a very small number of confirmed DOE-GNs, especially on kiloparsec scale, smaller. And there are two major difficulties in observing the systems. So first, the really small separation between the massive black holes requires very high angular resolution to distinguish them as a dual. And then there's the significant gas obscuration at the center of the galaxy due to the merger, which will block the system from our view. And there's another challenge arise from cosmological simulations that attempt to model the formation and evolution of DOE-GNs. This simulation often lack the resolution needed to calculate the observational properties of DOE-GNs. And the cost of increasing the resolution is just too high, like we just saw in Astra simulations, very expensive. So we built a semi-analytical model, SAM, try to solve this problem. So our SAM have M1, which is the primary black hole fixed at the center of the galaxy remnant, stellar barge around it, stellar disk, gas disk, and we have M2 secondary orbiting the primary in the disk plane. So we're basically looking at a 2D problem in the disk. In each simulation, we put our secondary 1 kiloparsec away from the primary, and the simulation stops when the separation reaches below 1 parsec. So we assume our primary occurs at bounding rate, and we also assume its luminosity does not exceed 10% of the Addington luminosity in order to match the typical values found in the X-ray surface of DOE-GNs. And for M2, we just assume they occur at Addington limited bounding hole ellipse rate. So in the decay, the dynamical decay process, we take into account both the stellar and gas dynamical friction. And we, for the stellar one, we include the dynamical friction from stars moving faster and slower than the secondary massive black hole following the model in Antonini and Murray 2012. And for the gas dynamical friction force, we use the model in Kim and Kim 2007, which break the locality and take into account the spiral shape of the gravitational wave trolling M2, which basically is due to the orbital motion of M2 around M1. So for each model, we have 5 key parameters listed here. And by varying each of them in their range of interest, we build a parameter space for theoretical interest that give us about 40,000 pair of massive black holes in different galaxy models. So here, observationally, the ability to successfully identify a pair of DOE-GN using the direct imaging method depends on both the separation between the two massive black holes and also their luminosity ratio, where larger values will increase their chance of detection by the direct imaging method, stressing the method here. So here we're looking at the 2D probability distribution of a pair of a DOE-GN with relatively low pair mass, low mass ratio, and in host galaxies with low slow rotating gas disks. So y-axis here shows the luminosity ratio, x-axis shows the separation between the two massive black holes. What the color bar is the fraction of evolution time or decay time in the entire simulation. So this can also be, you can think this as just the probability of observing the system. So you can see by the hottest pixel in this plot that this pair is most likely to be observed as a DOE-GN at a separation of 400 parsec and at a separation and at the luminosity ratio of 10 to the -2. And here, sorry, here we're seeing the same plot but for another system with relatively higher pair mass, more comparable mass ratio, and in system with faster rotating gas disks. And in this case, we see by this pixel here that this system is more likely to be observed, most likely to be observed at separation of around 700 parsec and at the luminosity ratio of 1. So both quantities are higher compared to the previous slide, right? So by this comparison, we show one of the key findings in the study that the DUAGNs are more likely to be observed in systems with higher pair mass, more comparable mass ratio, and in systems with fast rotating gas disks. And strengths that this is using the direct imaging method, not other like variable, periodic or spectrum. So overall, we expect configurations that leads to long-lived, widely separated DUAGNs with high luminosity ratios to be most likely to be detected by the direct imaging method. So here we combine the most likely separation, most likely luminosity ratio. These values are just what we got from this pixel plots. And also, here's the evolution time spent at this combination of values to be the detectability of a DUAGN. And please don't think too hard on the absolute value of this detectability. These are meant to be relative quantities that we can compare to each other and see what galaxy property holds the most likely, most observable DUAGNs. So here we show all the detectability of those 40,000 pair of DUAGNs. X here is the bulge mass, and here is the gas fraction. I'm sorry if people can't see on the right side of the room. The left is bulge mass, right is gas fraction, and the color bar is the most likely luminosity ratio. So as you can see by in these two plots, systems, DUAGNs in host galaxies with bulge mass smaller than 10 to 10 solar masses or gas fraction larger than 0.2, illustrated in these two red circles, have the highest detectability. And this is just because from the dynamical aspect, these systems dominated by the gas, in their decay process, their evolution is dominated by the gas, dynamical friction alone, while the other, compared to the other systems, the rest of the systems, those process is dominated by both, is driven by both the stellar and the gas dynamical friction, so larger. So that means this system in the red circles have longer evolution time, which makes them shine as DUAGN for a longer period of time. And that's why they have the highest detectability. Meanwhile, this system, as you can see, they have high gas fraction. They usually have really high gas density, and that will boost their accretion rate, also luminosity. And that will, that's another reason for them to shine, to be more detectable in this case. All right, so this is a meeting. We heard a lot about feedbacks already. So now what if we add in feedbacks? So we have heard a lot about radiation feedback, jet and all the stuff, but I want to stress that radiation feedback can also have influence on the dynamics of massive black holes. So for instance, we find this negative dynamical friction phenomenon in which we find that the radiation feedback can actually reduce the magnitude of gas dynamical friction force by about 40% and also reverse their direction, which means it's actually accelerating the black hole instead of slowing it down. In this case, the radiation feedback acting on the dynamical aspect will increase the massive black hole binary coalescence time and also decrease their coalescence rate. You can find more details in our paper here, but in this exercise, we know that this negative dynamical friction will hold the two black holes as binary for longer time, which will actually increase their detectability of DUAGNs. On the other side, we have this radiation feedback suppressing our accretion rate and also suppressing the luminosity. So in summary, radiation feedback has two aspects. First, on the dynamical aspect, it will actually increase the decay time, increase the detectability. However, on the other side, the suppression on luminosity is just severely stronger than the first effect. And this combination will actually result in the overall negative effect on the detectability due to the radiation feedback. So this is just showing what I said. This is a comparison of detectability. Top, you have seen this a couple slides ago. This is without region feedback. The bottom's the same plot for the same DUAGN population, but with region feedback, both aspects as I mentioned. So as you can see that even though we have dynamic refraction, negative dynamic refraction increasing the detectability, the overall decrease in luminosity will just make the detectability lower in the presence of radiation feedback. And especially the suppression is most severe in this gas dominating system because radiation feedback only affect gas component in the system. And those are the dominating factor in the system circled here. All right, so far we've been looking at just the statistical study of mock galaxy models. And now we can use our SAM on the data of illustrious TNG and try to predict the massive black hole binary coalescence rate and also DUAGN coalescence fraction. I'm speeding up here. All right, so here we show that we count the number of DUAGNs that become coalescent at redshift 0 and plot the coalescent fraction of DUAGN in the left panel here. As you can see by the comparison of the green, blue, and cyan curves, this is different DUAGN population with different initial separations, green for 100, blue for 400, and cyan for 700 parsec initial separations. As you can see by the comparison, the coalescence fraction of DUAGN goes down as the initial separation goes up, and also it goes down as the redshift goes down. And this red curve is the money curve here, that it's the general coalescence fraction of all DUAGNs in our parameter space. And on the right, we see the corresponding LISA detection fraction of the DUAGN population here, assuming a signal to noise ratio larger than 8 to be detectable by LISA. So what can we do with this? We can actually, one exercise is to calculate or estimate the coalescence rate using the coalescence fraction shown in the previous slide. So using this equation here, F col is what we are seeing in the previous slide, the coalescence fraction of DUAGN. This N DUAGNs and co-moving DUAGN number density. Hopefully we can get this from observers. And the DL here is the luminosity distance. So this is in the effort of trying to connect between EM observation and gravitational wave detections. All right, here is my summary plot. Marta's catching on me here. So this is basically the take homes. In the right, I basically show a methodology of finding the properties of galaxies which are most likely to host observable DUAGNs. And this is my thank you page. Here are the publications from this exercise. If you're interested in those, you can read. And also, I want to thank all the organizers of this wonderful meeting for and also those fruitful and inspiring discussion sections. Those are really good ideas. And here on the left, it's my team. It's my mental health team here. So have a wonderful day, and I will take any question you may have right now.
Time for a couple of questions.
Thank you for the wonderful talk. Is the presence of a disk necessary to observe dual AGNs? Like very, I guess, open-ended question.
No, it's not.
That's just what you focused on.
No, it was just easy to build a galaxy like that. And because we're using the Kim and Kim 2007 model for gas and refraction and feedbacks, those are 2D models. So we can only put a disk there for this.
Thank you for the talk. So you showed that the large scale separated dual AGN are less detectable, right, with the radiative feedback. Is that right? Did I get this right? No? Wait, you showed how they were missing?
Which plot?
Oh, that it got a bit fast at the end, so maybe I missed this.
I'm sorry. This one?
You showed no.
Oh, you mean this one?
Yes. So they're kind of missing. But then at subparsec scales, we might see them with LSST and transient surveys, right? So do you think there'll be a mismatch with the dual AGN we see at large scales and then the binary AGN we see at small scales?
I think that's a really interesting point because currently we're stopping at 1 parsec just because the dynamic reflection dominant toward onto that separation. So we just stop there. But it's a very interesting point to use because this is direct imaging method. It's just not at small separation. It's just impossible to see them by the direct imaging method. But this is a methodology which can be applied to different observing technique. For example, like what you're saying there, so for different observing technique, we have different observables that it's important in that technique and which can be kind of switch gear and make a new model toward a different observing technique. And that's something
it could
interesting.
cause some headaches if we don't see them in large scales, but then see them in small scales. Like, it would be weird.
Right.
Yeah, thanks.
So it's a good combination, like it can be added to this detectability.
Let's thank Lily again.